this is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at differences between effusion and diffusion for gases and really start to get into why the gas speed is what the gas speed, where do we get the heat 'em up, speed 'em up, why does Boltzmann's distribution look the way that it does when it changes temperature or when I change the molar mass of the gases. All right? Okay, so first off, before we even get started into what diffusion and effusion are, what we need to do is actually get into defining what molecular speed is for our gases. Now, to do this, what we're going to do is we're going to take a look at Maxwell's equation. Maxwell's equation, what it does is it's going to look kind of complicated, but really all it does, it just describes how fast a gas particle is moving. So we're going to define it as a root mean square velocity, V-E-L-O, there you go. And I'm going to abbreviate it as VRMS. So VRMF is the root mean square velocity, and it is equal to the square root of 3RT divided by the molar mass of the gas. All right? In this particular case, the R value is the ideal gas law constant, and in this case it does have to be 8.315, and that's joules per Kelvin dot mole. And it has to be that R value because kinetic energy is involved. Remember, the kinetic energy of the molecules is determined by how fast they're moving, and that is the Kelvin temperature scale, right? Okay, so what you see here is that this actually mathematically explains that heat 'em up, speed 'em up, right? So if the temperature, which is on top of this particular equation, if the temperature gets larger, then my velocity will actually get larger, right? And so that does explain the heat 'em up, speed 'em up. It also explains that idea that a bigger molecule is a slower molecule, because look at where your molar mass is at. The larger the molar mass gets of a particular gas molecule, the smaller the root mean square velocity actually becomes. And so this equation, Maxwell's equation, actually explains Boltzmann's distribution for molecules at different temperatures, right? The average kinetic energy, as the temperature goes up, I have more molecules that are moving faster, right? And then also explains it for Boltzmann's distribution of molecules with different molar masses, right? And we see as a molecule gets heavier, the number of molecules that are spread off of the average are actually getting smaller, right? Okay. So here we go. Now that we have an idea of what molecular speed is and how we mathematically define it, we understand the relationship with temperature and with molar mass, we can start to define what effusion and diffusion actually are for gases. So the first one that we're going to look at is actually effusion. Now I'm going to pause this video because I need to draw a box. All right? Okay, so I've got my box drawn here. Notice I've got two compartments in my box, and what I'm going to do is I'm actually going to put a pinhole right there in between, and then I'm going to place a gas in the left side. We'll call it side number 1. And so what I'm going to do is I'm going to place a gas and just let it sit in there, and then the effusion is actually, the definition is passage of a gas through a tiny orifice, or a very small hole, right? That's why that orange dot there, that pinhole is there, because what we're trying to do is figure out how fast do these molecules actually make it through the pinhole, right? And so the effusion is moving through that. Now, think about what we just learned with Maxwell's equation. The faster those molecules are going, the more of a chance they're going to get to actually hit that pinhole and make it through, because the more times they will approach and actually have a chance of going through. So heavier molecules generally have a slower effusion rate, right? So heavier molecules generally have a slower effusion rate. And we can actually mathematically describe this as well. The rate of effusion for molecule 1 divided by the rate of effusion molecule 2 is equal to the square root of the molar mass of 2 over the molar mass of 1. Now notice this is kind of a tricky way. I do 1 over 2, then on the other side it's 2 over 1. And what it'll do is just give you a ratio if I'm comparing two different gases of how many times, what order of magnitude is how much faster one gas will diffuse than the other. And this becomes really important. Believe it or not, effusion is one of the major ways that and most common ways that we actually purify gases. Right? You ever wonder how they get oxygen into a tank and say, hey, it's pure oxygen? Well, a lot of the times they're using effusion techniques to actually isolate that oxygen molecule away from other gas molecules, right? So effusion is a very, very common method for us to be able to isolate and purify gases, okay? All right, the next one that we're going to do is we're going to look at diffusion. Now, diffusion is just the rate of mixing. Right? So how fast will gas molecules actually mix? So the most common and the most tested topic is I have a tube. At one end of the tube, I'm going to put a cotton ball filled and doused in NH3. On the other end of the tube, I'm going to put a cotton ball that's filled and doused with hydrochloric acid. Now, both of these will enter into the gas state under these particular conditions, and I understand that NH3 plus HCl will actually make NH4Cl, ammonium chloride, which is actually a solid. So I'm going to take these two gases and I'm going to form a solid. And so the question becomes, if the tube is empty, where does my solid form? Does it form here? Right? Does it form directly in the center? Does it form over here towards HCl? So where are we going to see this particular solid form? And so if we really just think about what we know with molecular speed, I know the molar mass of NH3 is about 17 grams per mole. I know the molar mass of chlorine is about, 36 grams per mole. Right? And so I would expect NH3, especially based on Maxwell's equation, I'd expect it to be a lot faster, right? And so would we say that they would mix here? No, because that means they're both going to be traveling, right? I've got NH3 gas traveling that way. I've got HCl gas traveling that way. If they met in the middle, then what that means is that your HCl and NH3 are traveling at the same speed. And we know since they have different molar masses, they're not traveling at the same speed. Right? I know that it's not going to hit over here because my lighter molecule should be the faster molecule, right? So a lighter one should be faster, and what I would say, if my solid formed over here, then I'd say HCl is moving a lot faster than NH3, and that's not actually the case. And so what we actually see is we see that solid, and it's really cool. You'll actually see a solid plate just kind of form there where the gases start colliding with each other in that space, right? Okay, there is a mathematical way that we can do this. We can also say distance of NH3 versus the distance, and this is going to look very familiar in a second, of HCl is equal to, you bet it, in molar mass of HCl over the molar mass of NH3. So notice what we did is we actually reversed it. It looks very similar to our rate of effusion equation that we just put in. And so if we actually plug these numbers in, and you can do that on your own, you'll see that it equals 1.5. And so what that means is that NH3 will travel 1.5 times farther than HCl will under similar conditions. All right? Okay, but you actually don't need to I don't know that you'll ever have to solve that out, but you will have to conceptually reason where my gases are going to mix, and that's really based on the molar mass, and you're using Maxwell's equation for that, okay? All right, ladies and gentlemen, if you have any questions, make sure you got them down. I'll see you in tutorials for those. Otherwise, I will see you in class.